Well, welcome back to CS 340, Machine Learning Data Mining. I'm your host, Brian. Co-host Payman. It's fall 2020, and we're going to talk about gradient descent today. But first, let's review what we talked about last time, which was the change basis for linear models, which changes them into something entirely different, way more powerful. Basically, linear models for modeling nonlinear relationships. So last time we talked about what we called a change of basis, right? Where, for example, we talked about polynomial basis, where we replace our original data matrix X, right? And we did this in one dimension, so our data matrix X is just n by 1, so it's not so interesting, but we'll get there soon enough. With a different data matrix, or a different basis Z, where we added a 1 for the bias term, constant. We added a, the data itself as another term, and then we started adding polynomial terms up to some order P, right? And what we said is that, in fact, we can fit nonlinear relationships, input-output relationships, with our standard linear regression model. And we introduced this different parameter vector V to indicate when we're dealing with a different basis, and Zi as being one of the rows of our new data matrix Z, okay? So basically what you do, you just treat Z as your data, and then you fit a linear model. And when you look back into the original feature space, right, and you look at the W's, right, and the features in terms of the original X's, right, then you have a model that is that basically is a polynomial relationship between the input and the output, right? If you plug n x into this equation right here, the value of that is some polynomial. So here we have a low degree, a first order polynomial, right, fit to this data. And here we have a higher order polynomial here, a degree 7 polynomial fit to this data, okay? So this is the same thing again, right? We have a low order polynomial here at the line, and then we have a higher order polynomial here, which arguably fits this relationship between input and output better. Obviously, if you have more than one feature, right? So if xi is, xi1 to xi d, I guess, right? We've been talking about one-dimensional, then we'll just say here, like if with a second order polynomial, in addition to the square terms for each of the features here, right, you might also want to include the cross terms.
Can we ensemble stack regression polynomials of polynomials?
Can we ensemble stack regression polynomials of polynomials? So sometimes the ideas that come out are so lovely. It's yeah, good question. Okay, so what are polynomials of polynomials? So indeed, right? So you can imagine you have your x to z, and then so we have our x to z, and then we have some weight vector v, and then maybe if you had a stacked representation, this outputs, I don't know how we would stack this, but you could imagine some different polynomial basis over here, and you stack them, and then you learn a polynomial basis on top of these. Yeah, okay, so basically what you're doing is you're inventing deep neural networks. Right. What will end up happening is it will need to put a nonlinearity here, but as soon as you do that, then you've got deep neural networks. So We'll get there. Take your time. Let's be happy for now. Okay. With this change of basis thing terminology, right? So instead of a nonlinear feature transformation, sometimes in machine learning we use the expression change of basis, right? And you can think of the zi's as being the coordinates and a new basis for the training examples. Of course, change of basis means something different in math, like when you actually do a rotation, that's a change of basis or something like that, right? In math, the basis vectors must be linearly independent, i.e. there's got to be 90 degrees in between them, right? In machine learning, we don't care. These things can be whatever, like our basis vectors can be linearly dependent in some way. That's fine. In math, a change of basis technically spans the same space, right? In machine learning, we're going to change spaces, right? So when we go from the x basis to the z basis, we're actually changing the dimension of the representation, right? The point is they're not a basis per se, right? They're a span, right? Or the span of, like, you can think of the span of the dimensions in feature space, but it's not a basis in the technical sense. We're saying that we actually say it differently, right? We talk about a basis as being basis vectors and the basis vectors span some space, and that's it, right? So unfortunately, we say change of basis in machine learning frequently. So if I say change of basis, think nonlinear feature transformation. That's it, right? So x to z, we do something, right? We're changing the coordinate system, the dimension, the everything in which that we use to locate a data point, or put a data point out in some feature space, in space somewhere. We've already talked about this change of basis notation, right? So we did linear regression with original features. The original features were x, that's our n by d data matrix, and w are our parameters in that case, right? And we find the d-dimensional w by minimizing the squared error that we talked about before, where we look at the difference between our prediction for every data point and the true value for every data point. Take a norm, square the norm, so on and so forth. Linear regression of the nonlinear feature transformations, we use z as our n by k. So k is the new dimension of the basis, right? Data matrix. And v are our parameters, right? And we can find the k-dimensional v by minimizing this squared error, which looks basically the exact same. Here, the y's are the same, right? But we're operating with z instead of x and w instead of v. That's it, right? No big deal there. Okay. So I think this section in particular was really ahead of the curve, so to speak, in understanding what's going on with the fitting polynomials of higher and higher degree, and how this impacts the fundamental trade-off that we discussed earlier in the course, right? So as the polynomial degree increases, training error goes down, right? So here we have a constant only regression surface. Here we have a linear regression surface. Here we have a quadratic surface. Here we have a cubic surface. Note that either this has to happen or this has to happen in the extrapolants, right? Here we have quartic function, so on and so forth. And once we have enough parameters, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8 parameters, right? And there are 1, 2, 3, 4, 5, 6, 7, 8 data points. We now have a model that's flexible enough to actually perfectly interpolate the data with no error, right? But if the actual data comes from an actual input-output relationship that actually looks like this, so the green points that show up here are new test points, right? Then our approximation error won't always, because it could be that the relationship is actually, 7th or 8th order, right? It won't necessarily always go up, but it's very, very likely to go up, right? We will start overfitting with a large enough p, right? That's basically true, particularly if the input-output, if the input-output relationship is simple, right? There is some sweet spot, which is, second, third, fourth approximation to what's actually going on, right? And the usual approach for choosing the order of the polynomial, if you're going to do just polynomial bases, to like selecting degree is to do cross-validation, basically. Look at a validation loss, do cross-validation to select the order of the polynomial, okay? Of course, I think people in this section also pointed out that polynomials are not the only possible transformation, not by a long shot, right? You can stick in all sorts of other basis functions. It turns out that I think in the current midterm examination, you should definitely pay attention to this one. That's a little bit unfair because we made that decision in between classes with the other section. If you have friends in that other section, don't tell them what I just said because you have an advantage now. Just kidding, tell them, please. So they're not the only possible transformations you can do with the data. And if you're going to do sort of old school machine learning where you try to manually, I shouldn't say old school, that's too negative. If you're in the situation where you have relatively little data and you have to do feature engineering that's science or intuition or knowledge based, then you might choose bases that are more rationally motivated, so exponential, logarithm, trigonometric functions, so on and so forth, right? And of course, choosing the correct nonlinear transformation, change of basis, can and often will vastly improve performance. So say, for instance, if you have data that looks like this, as always, inputs on the horizontal axis, outputs on the vertical axis, then you probably want some sort of trigonometric basis here, right? So you might want to transform to a z that actually takes, for instance, the sine of the feature, right? So that the ultimate regression function ends up being some weighted sine, right? So like this, right? So here's our prediction. It's V transpose Z. V transpose is just W1 sine of X, right? So this basically would allow you to scale, for instance, that particular basis expansion would allow you to scale a sinusoidal feature. Of course, you could actually put different features in with different frequencies by simply, making, sine of, 2x1, half of x1, so on and so forth. And then you would have features that have different frequencies, right? And you can select amongst them by, fitting. Some of them will be zeroed out. Some of them will have high weights. Okay, cool. Of course, you can keep going like this if you have some sort of, there's a famous data set called the airline data set. It's basically air passengers over some period of time, and there's a periodic thing where you have more passengers in the summertime, so on and so forth, but a linear growth trend, right? So you can fit data that looks like this in one go if you expand your basis to include like, for instance, a linear term and some sort of high frequency sinusoidal term. Okay, so the design of this particular basis, by which I mean picking intelligently the features that you include, can really change how well your model does. Okay, and here we're not talking about learning these bases. We're not doing stacked polynomials, so on and so forth. We're just saying, okay, let's fix this. Let's pick it intelligently, and you can do pretty well. Any questions at this point? Either I've put everybody to sleep, or I've been exceptionally clear, one of the two. I'm going to go with exceptionally clear today. It seems too easy. Okay, great. Awesome. Okay, so yeah. So we're now going to move into like the next main, so like linear models are super.
How would piecewise function be represented in matrix form?
Okay, so yeah, okay, so this function here, whatever this is, can be whatever you want, right? So that's maybe not a bad call, right? So if you know for some reason that you think that as a function of like the impact on the output for some particular feature happens to, you know, look like that, right? You can impose, you can say that, oops, this is just some function, we'll call it f of xi, right? That's fine. That can be a feature that you stick in. That's totally fine. Now you have a piecewise relationship between, like basically you have this as one of your features, and that's fine, right? Okay, that's easy, cool. Okay, so let's move on to, so we've got linear models now, and the change of basis is an incredibly powerful technique and realization that you can use linear models in like plain Jane, plain Joe, linear regression technology to fit nonlinear relationships. That's pretty cool, right? But the way we fit them or optimize the parameters was potentially pretty costly, right? So we actually solved a linear system to find optimal parameters for the regression model, right? And that's cool when you can do it, but quite often in machine learning, you can't do that. So the question is, how do we deal with that, right? So we're going to talk about optimization a little bit more explicitly than we have so far. So let's establish some terminology. So when we minimize or maximize a function, we call it optimization, right? In least squares, we want to solve the following optimization problem, right? We want to minimize this function, right, over some space here, d-dimensional real valued vectors w, right? And there are two things that we could ask for. We could ask for the minimum value, or we could ask for the w that minimizes the value, right? This function over here is called the objective, right? It's also sometimes called the loss or the cost, and these, you know, there can be likelihoods here, there can be elbows, there can be all sorts of things that are called there, but there's some objective function. And the set over which we search for an optimum is called the domain. Right? And usually, instead of the objective value, right, the minimum value of this function achieves, right, we actually want a minimizer, right, which is to say the argument which produces the minimum function value or objective value, right? In this case, it's going to be a set of parameters that achieves the minimum value of our least squares loss. So we've seen some examples of continuous optimization already, right? In least squares, the domain is the real valued set of parameters w that live in, again, RD, right? The objective is the sum of the squared training errors. Right? That's what we've written down all the time. We've looked at discrete optimization as well. In particular, when we fit a decision stump, the domain is the finite set of unique rules. And the objective is the number of classification errors. Of course, I talked a lot about the combinatorial optimization, greedy part of that, which is also a discrete optimization problem. But the discrete optimization problem has a very, very, very large number of discrete bends, an exponentially large number of discrete bends. We've also seen a mixture of discrete and continuous optimization, right? So if you look at the k-means objective, it's continuous with respect to the means, which means that you could use gradient descent techniques to fit the means. But it's discontinuous with respect to the cluster assignments, which means that you need to do some sort of discrete optimization. And there we have that's the greedy part of the k-means algorithm, where we just greedily assign to the nearest mean. But the overall thing that we're trying to do is actually minimize the k-means objective cost function. We'll use terminology like stationary or critical points throughout the course. So a W, and here we're just going to stick with our linear regression terminology, right? With the gradient function of our objective with respect to W evaluated at w equal to 0 is called the stationary point. So that point w is a stationary point or critical point. Right? And this is, we've already established, is a point where the slope is 0, so the tangent plane is flat. Right? So all the stuff pointed at in green, including this entire region, those are all critical points or stationary points. Right? We're going to call certain sets of these by different names. Right? We're generally interested in either a local minimum, a global minimum, or a global maximum. Often we're going to be minimizing, so we're going to look for the global minimum, which is some kind of local minimum. There's a local maximum, local minimum, local maximum, local maximum. Here's a region of critical points, all local minima. Here's an inflection point, right? Fine. Cool. Okay. When we're minimizing, we would ideally like to find a global minimum. That's not always going to be possible, right? In linear regression and with a least squares objective, it is. But for many problems, in particular, all the problems in deep learning that we'll run into, that's not going to be possible. So the best we can do is find some stationary point where the gradient is equal to 0. And quite often what you end up doing is you, again, run restarts of gradient descent, which we haven't really described yet, but you're going to run restarts and then pick the stationary point with the lowest objective value. Okay. Cool. So to motivate gradient descent, which is what we're working up to right now, let's think about large scale least squares, right? So what we said, and the way we went about solving the least squares problem, which is applicable for nonlinear regression and linear regression, all that sort of stuff, is that we derive the normal equations, right? Basically by setting the gradient of the least squares objective, the gradient function of the least squares objective, equal to 0, right? And when we can solve that for the w that makes this happen, right, in O n d cubed time, right? And we went through this before, but basically when we set the gradient equal to 0, we have these normal equations, and then constructing x transpose x was an nd squared operation, constructing x transpose y was an nd operation, and then solving a d by d system is an od cubed operation, right? So if d is large, and now that we've talked about polynomial regression and expanding our basis set and these sorts of things, you can maybe start to imagine that having d large is a powerful thing to do. Like we still have in our mind that this is probably going to overfit. We're going to figure out ways to make it not overfit even when d is really, really large. Okay. So we're going to quickly be in the situation where we're going to make really, really, really big d in order to be powerful, and we're still going to be able to actually work with a model. Okay. So we need to be able to actually fit such models when d is large. Like, you know, if d is 1,000, this is a pretty big number, right? Okay. So an alternative when d is large is basically gradient descent, right? And this should probably be in red or with exclamation points or something like this. In modern machine learning, gradient descent is probably the most important class of algorithms that we're going to see and use. And it's super simple, right? Should be familiar to most of you, actually. If it's not, it will be after this, right? So how do we use gradient descent to find a local minimum, right? So gradient descent is an iterative optimization algorithm. It starts with some random guess about the parameter vector, just random numbers in w, right? Then it uses the gradient function evaluated at that guess to generate a better guess, w1. We'll just call it w1, the next iterative of the algorithm. And then it uses the gradient evaluated at that iterative of the algorithm to get a better guess, w2, gradient at that to get w3, so on and so forth. And gradient descent has a property such that under certain circumstances and restrictions and assumptions, right, the limit of this process of updating our weight vector as t goes to infinity has the gradient of the tth iterate as t goes to infinity in this algorithm, this gradient is equal to 0. Okay, so basically, if you do this, you're going to get to a local minimum. It converges to a global optimum if f is convex. Okay, and we're going to talk about convex functions near the end of the lecture today. So gradient descent is based on this very simple observation, right? So given parameter is w, the direction of the largest decrease is in the opposite direction, like, of the gradient vector at w. So we're going to do this in one dimension. It sort of holds in multi dimensions. You don't have to think too much about it, right? So here's our objective function f. Oops, sorry. And here is its parameter w. Okay. W naught is our initial guess of the parameters. It's the start of our gradient descent algorithm. And here's the function evaluated at w naught, right? So, and let's say, for instance, this point here is the minimizer w star. Yeah. Okay. So if we evaluate the gradient function at w naught, it returns the slope of the objective function at that point. So we can produce a first order Taylor approximation to the function.
Is there a reason gradient descent is so prevalent?
Yeah, so let's punt on this for just a little bit. That's a little bit beyond where we are. So let me go a little bit further before I address that question. Yeah. So so if we have a first order approximation to the function, which takes value fw naught and then has slope grad fw naught, right? Then right, that the direction in w space here that you need to go is this way, right? And that's opposite in sign to the sign of the gradient, right? So the gradient or the slope or whatever here is negative, and we want to move in a positive direction in w, right? So what do? The slope at grad, here is negative, so we can decrease f of w by making w more positive. Okay, that's what we do, and that gives us w1. And let me do the right thing here actually, and I think I can do this. I used to be able to do this. Yeah. So if we move in that direction, so we can decrease, we can iterate gradient descent and move to w1, right? Cool. Then we do the same thing. We compute the gradient or slope of the function at f of w1. We construct the first order approximation. We see that the slope is negative, so we want to move against the slope. And we select a new point, w2, and that makes w more positive, and so on and so forth. Decreases the function value. We keep doing this.
How much do we increase w?
Nice. And how does this work for more dimensions? Okay, cool. Okay, so, and yes, notationally, this is not w to the power 0. This is just the the iteration number of the algorithm. How do we know which direction to go in multiple dimensions? If you remember, the gradient function is a vector field that produces the tangent at that particular point. And basically this negative applies to all dimensions of the gradient vector, right? You just want to move in the opposite direction. So you take the entire gradient vector and you just want to go exactly the opposite way, okay? Yep. And Yes. How does determining the direction? Oh, no. So how much do we increase W by? Okay. So that's going to be the step size. And we're going to talk about that in just a little bit. We haven't got there yet. But that's an area of active research. But here we have a pretty good idea of what to do. Okay. Before we get there, I want to point out that we can actually step past the minimizer, the global minimizer, right? And if we do that, that's okay. The slope here would be positive, right? So we still want to move in the opposite direction. So we move in the negative direction, right? Oops, sorry, I'm going the wrong way. And that means that our next iterate will move in the other direction, okay? So we can bounce around, basically. That's the point, right? We can move this way, and then we can move this way, and we can move this way, and we can move this way, and so on and so forth, okay? Cool. So now the next thing is how far do we move? And that's this step size, right? So we're going to pick alpha naught to be small. And one way you can do this is to just pick a number that's small. Another way that you can do this is you can monitor the sign of the gradient and see when the sign switches. Another way you can do this is to do a line search up to and step only as far as the function itself goes down, right? There's a whole slew of different algorithms that you can develop. Here, let's just say you pick a value that happens to be small enough, right? Such that f decreases, right? And obviously, if you pick alpha to be really, really, really small, then if it's infinitesimally small, it's going to decrease because that's the definition of the gradient, right? So usually what happens is you start with some guess for the value of alpha naught, 0.001 or 0.01 or something like that. And then you decrease it if you find that the function value actually increases. Okay, so that's this Feynman in the homework materials. So then you repeat this to successively refine the guess, right? And here, notice we've chosen, it's not super important, but there's going to be a different, you can change the learning rate per iterative of the algorithm, right? And usually you'll decimate the learning rate as you go in order to achieve convergence, okay? So this is the full algorithm, right? So you compute the gradient, evaluate it at the current weight vector, move away from the gradient direction by some step size. That's it. That's gradient descent. Easy, right? And you just do this for t goes till whatever you want, up to some termination condition. So one way to stop is to actually monitor the function value itself and see that you're not making any additional progress in minimizing the function. The other way is to actually look at, say, for instance, the magnitude of the gradient vector. And if the norm of the gradient vector is below some threshold, you just say, that's good enough. We're near an approximate local minima, and that's fine. So we'll, so the question is, alpha usually constant, or do we want to decrease it as we progress? Generally speaking, you will end up decreasing it as you progress. Although different optimization theory makes different assumptions about what's going to happen, sometimes you don't need to. Alpha is the step size. That's how far you move in the direction of the gradient, right? So you have a choice here, right? We haven't said it when we were doing this, we had a choice. We started at W naught, and we said that we wanted to move opposite the sign of the gradient. That we could have moved this far, or we could have moved this far, right? And if we move this far, it's not so good because we're going to be way over here, and then we're going to evaluate the slope here, and then we're going to, if we use the same step size, we'd step even further over here, so you can actually diverge if you're not careful about step size. You can actually step out. So okay, great. You all have like, great. These are good questions. Can you try multiple values of alpha and pick the one that results in the best decrease? Well, again, we're going to want to have a sequence of alphas. it's probably best to pick a small one and then incrementally adjust it down. That's fine. So it can be positive or negative depending on which way you want to move. I wouldn't use a negative alpha because that would imply that you're moving in the direction of the gradient, which means that you're going to maximize rather than minimize the objective. And that's, maybe if you want to maximize something, that's the way to go. But if you want to minimize, then you want to go, yes, you can do gradient descent as well. And of course, you can change the sign of your objective, and you can do gradient descent versus gradient. We do gradient descent, and we think about things in terms of loss functions in this course. So we want to go down. We're going to make things small, drive things towards zero. Yeah. Okay. Cool. Oh, okay, cool. But before we get into too many more details, and we don't get into a huge number of details in 340 anyway, because gradient descent and stochastic gradient descent just generally work well, and they're the workhorses of machine learning. We'll talk about that in just a second. So one thing to think about is, like we're used to now seeing the regression plot in the X versus Y space. So here's X and here's Y. In the data space, right? But what we should be really thinking about is that we have two parameters, W1 and W2, which is, I guess, intercept and slope, something like that. And the curved surfaces here are F of W, where W equals, W1, W2. And this is, our least squares objective, sum over n 1/2 norm squared, right? Okay, so when we're doing gradient descent, we are actively seeking to minimize the sum of these errors, squared errors, but the objective function surface looks like this, right? It's this kind of bowl-shaped, in this particular case, we know that it's convex, which we'll talk about in just a little bit. It's a bowl-shaped convex function that we're trying to optimize in, okay? So, and just for the fun of it, this blue square is going to be well, eventually, now I guess it's red and switches color, great. So that will be the global minimizer. Okay, so in data space, here's what a particular slope-intercept pair looks like. Here's one possible line, right? In parameter space, that corresponds to a parameter here and a particular loss, right? So the gradient vector here, it's difficult to say, but it's probably going to be something like this, right? And what we'll do is every iteration of gradient descent basically tries to move the guess closer to the solution. So here's the second guess. This is what it looked like in data space. This is what it looks like in the optimization surface space. Here's another guess, and there's another guess. And that's what's happening. So we're moving around in this objective function space, right? And the corresponding thing is happening over here where this line is getting closer and closer to a good fit, right? to something that minimizes the sum squared errors. So again, if we think of this as our regression loss surface, right, our least squares loss function, right, here's our W naught, and it should be noted that all sorts of trajectories can happen, right? So the direction of steepest descent will not necessarily point directly at the solution. You can step past the solution and do things like this, but in general, you should think of gradient descent as something like almost like a random walk that actually gets you to an annealed random walk that gets you to a global minimizer. So, and these are the iterates of the algorithm. Again, these are not powers of W, they're iterates of the algorithm, and the minimizers here at the bottom, right? So the conditions that we'll think about, and we're not going to do this theory out in any detail at all, but basically you can show that gradient descent will converge in general to a W, which is a critical point, right? Where the gradient function evaluated at W is equal to the zero vector. If the function is bounded below, so in other words, the function can't diverge to negative infinity, which would mean that you need an infinite number of steps to get there, the gradient function is nice. It can't change arbitrarily fast, so that like if you make a small step, you could end up having a gradient that points you in some other crazy direction super fast, right? And
So this,
yeah.
this plot can have much more dimensions than 2. This is just for easy to plot.
Yes, yes, of course, yes. We're talking about 2 dimensions, but that's simply literally because it's the thing that we can plot, right? The gradient descent we're talking about, we're going to be doing this in 10 million dimensional spaces by the end of the course, right? Akeem, you're just you're just begging to be a machine learning researcher. So what's the cost of gradient descent then? It can technically iterate forever, correct, or it can finish in 3 or 4 iterations. Unlikely in most situations, except in convex situations, for convex objectives. The only it's very hard to make general statements. You basically can't make general statements. In certain classes of functions, if you sufficiently restrict the set of functions that you look at, they're convex. They have, they have Lipschitz bounds that are well defined and tight. Then you can start to make some assumptions about the expected runtime of the algorithm, right? But in general, in this course, we're not going to talk about that. And I would refer you to 540 for full coverage of that, right? Yeah. So there's, there's all kinds of zany optimization functions. There's a huge body of work in this. I've even written some stuff with Mark called type gradient descent, which is something Mark Schmidt is probably the foremost optimization, one of the foremost continuous optimization researchers in the world. And he would just bore the living crap out of you with details and different kinds of optimization functions that you could want to optimize and so on and so forth. Different algorithms that you would use to, for instance, choose alpha. But let's not get too bogged down right now because we want to at least solve least squares today, right? So least squares objective is this is what we've talked about for a long time, right? And we derived the gradient with respect to W of this objective, and it's this, okay? That means that gradient descent for fitting the parameters of a least squares regression model looks like this. So we have our iterates, we have step sizes, and we have the gradient function plugged in here. So this is the gradient of our objective with respect to WT. And that's pretty much it. Cool. Now the cost of gradient descent is order ND. We don't have to form this X transpose X matrix, right? So the bottleneck is computing this gradient function right here, right? Computing X times W transpose is order ND. There's N operations when you do the subtraction, and then there's another order ND operation here. So solving the normal system, like the system of equations set up by the normal equations costs this, right? Gradient descent costs this, where we don't necessarily know how long the overall algorithm is going to run, T, right? But it can be faster when D is very large, right? So if you can get to a solution that's good enough for a T, for instance, that's less than the minimum function of D and D squared over N, then you should use gradient descent, right? And you can show that the T that you need in this particular special case is related to the condition number of this matrix X transpose X. There's no direct dependence on D, but that means that like the number of steps is actually basically data dependent, right? It's problem dependent, right? And just to be clear, the normal equations, and this is something that trips people up every time, normal equations only solve linear least squares problems. In other words, gradient descent can solve lots and lots and lots of problems, right? But this particular gradient that we plug in here is the gradient expression for linear least squares, okay? So don't go off thinking that this is gradient descent. This is gradient descent applied to the linear least squares problem. Yeah. Okay. And there are many, I've already hinted at this, there's many variations of gradient descent. You can use line search to choose the step size. There are conjugate and accelerated gradient methods. There's Newton's method, which uses second derivatives. There's second order methods that attempt to be second order without actually estimating the second order quantity, which is the Hessian function. Right, and that's, if you think about what second order methods are going to have to do, it's pretty nasty because you have to build a second order approximation in a vector space, and that second order approximation is going to be d squared in size, and if d is large, you're pretty much hosed, right? What's more important is for us is stochastic gradient, and in this course we focus exclusively on gradient descent and stochastic gradient descent because they're simple. They really reliably give reasonable solutions to most machine learning problems. But you should be aware that if you're doing gradient descent, there are methods that are faster and you can use in some applications. Okay, I don't want to pause too long here because I'm basically out of time, but the next bit is really, really easy. What if we don't have the analytical expression of the gradient? That's a really good question. Only very, very occasionally does it make sense to do. There are, I forget what they're called. You can always get a numerical approximation to a gradient by doing finite differences or something like that. There are also more sophisticated methods for injecting random vectors into the objective function to get an approximate gradient. You can do stepwise optimization where you don't have a gradient for the entire parameter space. Objective functions that are not differentiable, which are some ones that I work with all the time, are certainly not in vogue. And I would say the last 10 years of experience in machine learning would suggest that efforts to avoid that by making your objective function differentiable is a really good way to spend your time. Okay, let's just do this really quickly. It's pretty straightforward. So is finding a W where the gradient is equal to the zero vector, the gradient to the objective evaluated at that point is equal to the zero vector, is that good enough? And the answer is yes for convex functions, right? So a function, as we said, is convex if the area above the function is a convex set. So all values between any 2 points of this means basically all values between any 2 points above a function stay in the function. Okay, that's cool. So that's convex, that's not convex. Okay, fine, that's not convex. So all W with grad W equal to 0 for convex functions are global minima, and we can prove this by contradiction. So let's consider some local minimum, right? If this is not a global minimum, then there must be a smaller value. Then by convexity, we can move along the line to the global minimum and decrease the objective. But then this contradicts that we're at a local minimum, right? And yeah, basically, end of story, right? So normal equations find a global minimum because the least squares objective is convex. Now, how do we know if a function is convex? There are some useful tricks for showing a function is convex. So a single variable, twice differential function is convex if and only if the second derivative of that function is greater than 0 for all W. So here we have our standard quadratic, right, function for a greater than 0. So we take the two derivatives, we have a, and if a is greater than 0, then this is a convex function by assumption. F of W equals e to the W, take the two second derivative, it's still e to the W, that's greater than 0 by the definition of the exponential function. So exponentiating is convex. A convex function multiplied by a non-negative constant is convex. So we have, this is convex, so 10 times that is convex. Norms and squared norms are convex. We're not going to prove that, but you can prove that. They're all convex. The sum of convex functions is a convex function. So we have 10 times a convex function, so that's convex. Here we have a norm, that's convex. There's a constant with respect to W, so this entire expression is convex. Inner products, convex, right? So each of these is a convex function. They're all, the second derivative of each term with respect to W is 0, so they're convex. Sum of those is convex, right? Conveniently, particularly for deep learning, max is convex. So if we have a convex function y equals 1 and a convex function y equals 2w and a convex function y equals w3, and we take the maximum of those functions, then that also is a convex set, is a convex function, excuse me. The composition of a convex function and a linear function is convex. So here we have y xw minus y is a linear function, right? Then f is convex if g is convex. That's pretty cool, right? Which means that when we do this, then our least squares objective is a convex function, right? It's not true that multiplication of convex functions is convex necessarily. So if f of x equals x and g of x equals x squared, if we multiply f of x times g of x, that's x cubed, that's not convex. And composition of convex with convex is, it's not necessarily true that that's going to be a convex function, that you have to decide that on a case-by-case basis. In other words, if f is convex and g is convex, then if you compose the functions by doing f of g of here w, this might not be convex. So here's an example. If x squared is convex and minus log x is convex, but minus log x squared is not convex, okay? Okay, so let me summarize real quick and then we'll answer the question. So gradient descent finds critical points of a differentiable function. It can be faster than normal equations for large values of d. That's critical, that's going to be very important for us. And it will find a global optimum if the function is convex and you set your step size sufficiently small. Convex functions are a set of functions with the property that this critical point that the gradient is equal to 0, that implies that W is a global minimum. And identifying what is or what is not a convex function can be usually done using a few simple rules and basically back compiling the expression. And next time we'll do a linear expression without outlier sensitivity. Okay, so I see there are a lot of, oh my goodness, lots and lots of comments here at the end. Okay, I think I'm gonna skip the vision-based stuff. Yeah, so I think we answered the analytical expression of gradient question. Yeah, so if you have a function that's not convex and could have many, local minimums as well as the global minimum, is that why we mentioned random restarts? Absolutely, yeah. So yes, in short, yeah, that's exactly why you want to. And there's all sorts of things that you can start thinking about, like momentum. You can imbue the gradient with momentum so that you can actually move through local minima and hopefully get to a global minimum, these sorts of things. There's all kinds, every idea that you could possibly think of in terms of like how to use gradients and use them effectively. Everything has been thought of, right? Yeah. What if a minimum occurs at a non-differentiable point? Yeah. Okay, cool. So, oh dear. So I'll say the following. So we will, in general, be dealing with functions that are smooth and differentiable almost everywhere, which means effectively that the set of the set of non-differentiable points is measure 0, which means that in any practical setting when you're doing gradient descent, you will never hit a point of non-differentiable, like you'll never hit a non-differentiable point, right? So you don't really have to worry about this this condition of, you know, if a minimum occurs at a non-differentiable point, checking whether or not the norm of a gradient is less than some value to stop the algorithm wouldn't work. The point is that we won't hit those points because there will be so few of them in the measure theoretic sense that we'll never hit it. Okay. Yes. Now we're getting into the minutiae, but it's actually important when you're developing these kinds of algorithms. These things you have to think about actually pretty hard. So Dominic says, but if our computer systems are finite, in other words, they use floating point representations of real numbers, the chance is still higher than for reals. Yes, but those also have finite precision, which means that yeah, I mean, okay, it's hard to say that, but like the classic example that we'll see in this course is ReLU, which is basically just a rectified, it's just a function with a kink in it. It's linear and then flat. Yeah, I mean, I suppose it can happen. Yeah, a 1 in 2 to the 64 kind of chance. Yeah, it's pretty small. The real situation is also that what we're really doing, if we really want to get into it, is we're going to be doing subgradient descent. So, right. So along with this measure 0 phenomenon, all of the analysis that we do we're sort of hiding the fact that we're doing subgradient descent such that the gradient is always defined even at the points of non discontinuity, right? So you can just pick one of the gradients at that point, and you're still fine. All of the theory for all of gradient descent still holds, basically. Isn't the absolute value function differentiable almost everywhere? In this case, when the gradient descent just never end. So again, with a decreasing step size, you will get arbitrarily closely tight to the minimum, right? That's basically what it comes down to, right? And again, you can, if you define the subgradient at the discontinuity to be 0, then you're totally fine as well. Which is what you would do in a real, like, automatic differentiation system and a real primitive for absolute value. You would have to define the gradient, the subgradient to everywhere. And you would define it to be flat 0 at the actual minimum, just in case you happen to hit 0 in your gradient descent procedure, in your 1 in 2 to the 64 chance of doing that, which does happen. Any other questions? Otherwise, I think we should thank payment. And oh, yeah, there's only 18 of you left, so that means everybody else has left satisfied, I guess.